Good afternoon, everyone. A warm greetings to one and all present here. It gives me immense pleasure to welcome you all for the virtual faculty development program on next generation AI, exploring the power of generative models and transformers, organized jointly by the Department of Computer Science and Engineering and Department of Cyber Security of Dr. MGR Educational and Research Institute. Today, Day 3 of our FDP, we will look into an exciting and insightful session on probabilistic generative modeling, latent spaces and distributions. We are privileged to have with us Dr.S Neelavathi Pari, Assistant Professor, Senior Grade, Computer Technology, MIT Campus, Anna University. To introduce Madam, now I invite Dr. S. Mohandas, Additional HOD, Department of Cyber Security, to give the brief introduction about today's speaker.
Ma'am, Sujita ma'am. Sujita ma'am. Sujita ma'am, are you there?
It's audible, ma'am.
Yes, if Mohandas are not yet joined, you introduce it.
1 minute, ma'am, 1 minute.
Ma'am, I will introduce, ma'am.
Okay, ma'am. Okay.
Ma'am, can you introduce?
Yes,
Yeah,
yes.
Good afternoon, everyone. Present here. I give me the ma'am. My voice is audible.
Yes, yes,
Yes,
yes.
It's give me the immense pleasure to introduce a remarkable academician and distinguished researchers, inspiring the mentor, Dr. S. Neelavathi Pari, Assistant Professor in Department of Computer Technology, MIT Campus, Anna University. Dr. Neelavathi Pari has been an integrated part of the academic community at Anna University since 2009. With over 15 years of teaching and research experience, she has contributing significant to the field of computer science, information system, wireless network security, IoT, and blockchain technology. Her deep experience has shaped numerous budding engineering, guiding them not only the academically, but it is also inspired them to involve is innovating and exploring the emerging technologies. She earned her PhD from Anna University in 2014, and even since she has been actively involved in the high impact research. Her work involved more than 34 publications, several of which are in the international conference and reputed journals. Her research contribution span from machine learning driven sensor communication to IoT based security frameworks and from MENet trust based routing to advanced smart system using embedded technology. Dr. Neelavathi Pari has also successfully completed several funded projects from Anna University. Okay.
Thank you, ma'am. Am I audible?
Yes, ma'am. It's audible.
Please join me in welcome to Dr.S Neelavathi Pari, ma'am.
Ma'am, just check, is my screen visible?
Yeah, ma'am.
Visible, ma'am.
And I would like to know whether it is moving.
Yes, yes, yes.
It is moving, right?
Yes, correct.
Yes, ma'am. Yes, ma'am.
So very good afternoon. And I thank the organizer for giving me the opportunity to be part of this FDP. The FDP topic, what was given us, the next generation AI. Okay, they're exploring the power of generation model and transformers. Ma'am, is the screen visible?
Yes, yes, ma'am. Yes, ma'am.
So based on that, so my topic is going to be the probabilistic generative modeling and latent spaces and distribution. So this is the content layout. So how the 2 hours is going to be. So we'll be talking about the probabilistic generative modeling. So what is the generative modeling? And I'll be talking few things about the probabilistic models, that is explicit density models, implicit density models, and the latent variable methods, how it is going to use for the prediction in the generative modeling. And then we'll be talking few mathematical concepts of the conditional probabilities, what is a joint probability and the marginal probability. And the next topic will be on the latent space and the distribution. So these are the topics what I'm going to discuss today. Okay, so first we'll be looking out into what is probabilistic generative modeling. Okay, the term says probability. So when we see, so we had learned in our school what is a probability means. So it is an event or the samples of sampling space. Okay, so how this generative model is going to use this probabilistic method for the prediction. So probabilistic modeling, it is a framework in the machine learning. So where we'll be able to generate the data and you'll be able to predict using the probability distribution. Okay, so instead of only predicting the labels, so based on the labels instead of predicting, so you know that the Google search, so how the Google search is made is based on the labels the search was being made. Okay, now we are going to learn the full probability distribution of the data. So allowing us to generate new sample, generative. So what if you're going to generate the new samples? So if there is a missing data or if there is any uncertainty in the data also, it has to be considered. Okay, so probabilistic generative model. So it is, the main aim is to model the probability densities or probability distribution that is going to generate the data. Okay, so here the main fundamental idea of this model is, so we are going to learn the joint probability distribution. That is, we are going to find the probability of x is given, that is a feature is given, and based on that x, how I'm going to generate z. Okay, p of give x given and how I'm going to generate x, or it is going to be p of x. And which can be used to generate new samples similar to the real data. So here, if I'm going to say joint probability distribution p of a given x, how I'm going to find the z is, x is going to be the any observed data. So it can be an image, it can be text, it can be audio, anything. And z is going to be the hidden representation, which will be terming it as a latent variable. So I'll be talking about this latent variable in a separate session. So here, this probabilistic generative modeling, the machine learning models, so we'll be classifying into, basically we'll be classifying into two categories. One is discriminative and the generative. So everyone has used the regression models. Okay, the regression model is going to be a discriminative. And how this generative model is going to be done using this probability distribution. So if you're going to see here, so once again. So if you're going to see here, what is it? How the discriminative model is going to be different from the generative model. So in the discriminative model, so the classifications will be done and you will be having a boundary line. A boundary line will be drawn. Okay. So discriminative classifiers learns the probability of given y with the x and estimate the parameters directly from the provided data. So here I have taken an example of the supervised classification use. And most of us know that for the discriminative, we'll be using the basic logistic regression method. And for the generative classifiers, here they are going to generate the estimated parameters. Here the Bayes theorem is used to calculate the P of y by x. That is the posterior probability. So let us understand this problem. So the data given us x is equal, these are the features x1, x2, xn, and the y can be, it belong to this or may not be. That is y is equal to 1 or 0. So we have to predict whether probability of y is equal to 1 given x. So in the discriminative approach, like logistic regression, so first we will be finding the decision boundary which would make. So decision boundary, how we are going to draw is it has to minimize the error. So whereas in the generative approach, where I'll be using the Naive-Bayes method, so you're going to estimate the parameters of P of x by y or P of y. Okay, use the Bayes theorem to calculate the posterior probability. Okay, posterior probability can be calculated in the generative way. So here I have taken an example. So if you're going to take, if you're going to see, you're having out the binary classification. Here we are having out two circles, blue circle and the red circle. So let me take that. I'm going to predict whether you are going to have a diabetic or non-diabetic. The only feature given is going to be the glucose level. That is, glucose level amount is going to be given. Okay, so here in the decision, so now wow, this yellow has been given, this yellow circle has been taken. So now we have to predict whether it will be in the class red or class B. So to which class it is going to belong. The discriminative method, what you are going to do is you will be drawing the boundary line. Decision boundary line will be drawn and we have to decide that we have to predict whether this yellow is going to be in the red or in the blue. Okay, so we'll be making out the decision so that the error rate is going to be less. We'll be minimizing the error and we'll be finding out this. Okay, so here I'm drawing out the 3 decision boundaries. So I keep drawing the decision boundaries such that we are going to minimize the error. Okay. So next we are going to do using this generative. So where in the generative model, so we are going to do the distributions of the data. This we are going to draw the distribution. So you are going to learn the distribution based on, we'll be checking out whether it can be a Gaussian distribution or non-Gaussian distribution or the normal distribution. Okay. And here if you're going to see, so any distribution, first we'll be having out this distribution. Then we'll be calculating the mu and the sigma. For the distribution of the data, we'll be calculating the mu and the sigma. And the formula what you're going to use is going to be you're going to maximize this with P of x by y of P of y by P of x. Okay, so we keep drawing out this line to yellow to which it is going to fit in. So if I'm going to take this, the distribution mean, if I'm going to take it here, so what is going to be the mu value and the sigma value? So we'll be finding out. So to maximize the distribution and to minimize your error. Okay. So you can see that for any distribution, we are going to draw the probability density function, which is going to calculate the mu and the sigma. So this is how the generative model is going to be generated. So some of the mathematical fundamentals what is required for this generative model is, so you will be training the generative classifiers involving the estimating function, that is x tends to y or probability of y given x. Okay, some a functional form of probability such as P of y or P of x given y. And with the help of the training data, we estimate these parameters can be estimated using the this probability function, and the Bayes theorem will be used to calculate the probability of y given x. And for the mathematics for the discriminative models, in the discriminative models we have to draw the boundary line. Okay, the training discriminative classifiers or the analysis, it will be involving the function x tends to y or probability of y given x. Okay, the x can be the feature. So based on that, I'll be calculating what is the probability of y. Okay, so some assume function that is functional form of the probability will be with the help of the training data, we estimate these parameters. Okay, so this is a general classification. So this is what has been given the difference. I have made a summary. So discriminative model is the generative model. In the discriminative model, it learns a decision boundary between the classes. So here I have taken only the binary classes. So you have taken your boundary decision is going to be done. So here what we have to do is we have to maximize the conditional probability. That is P of y given x. Then you are going to directly, you are going to estimate what is the value of y. We are going to predict what is y for the feature x. Okay, so here it cannot generate. So whatever the data I'm giving, that it can discriminate and say to which class it belongs. But it cannot generate the new data. Okay, so it is meant only for the classification task. Discriminative models doesn't possess any generative properties. Okay, so for example, the logistic regression, the random forest method, SVM, the neural networks, the decision tree or the k-nearest form, all these things are the example of the discriminative models. So when we consider the generative model, so generative itself is going to be, what it is going to tell is something new I'll be able to generate. Okay, from the existing data, I can synthesize, I can generate the data. Okay, so here it is going to learn the input distribution. Okay, whereas in the decision bound, it is in the discriminative model, it is going to where the boundary has to be moved. It is finding out where the boundary line, decision boundary between the classes, how it is going to draw. But in the generative model, it learns the input distribution. What is the distribution? So whether it belongs to this class or this class. So here, it is going to maximize the joint probability. So I'll be discussing something on the probability functions. So here you're going to use a estimate the P given x for y to find the probability of y by x using the Bayes rule. Okay, so here it can generate the new data. Okay. So they are not used to solve the classification task. Okay, so it is not purely for the classification job. So this generative models possess some of the discriminative properties also. So some of the examples are the hidden Markov models, Gaussian discrimination model, Bayes model, LDA model, so etc. Bayesian networks all follows this generative networks. So this discriminative model, so how it is going to learn the decision boundaries that is going to separate the different classes. So it has to maximize the conditional probability. So given the input x, so you are going to maximize the feature of the probability of the label y. It is P of y given for the feature x. So they are meant for explicitly for the classification task. Discriminative models is used for the classification. So some of the examples been given here. And generative model, it has to maximize the joint probability using all the features of x and y. Okay, it is going to learn the class conditional distribution, and they are typically meant for the classification task, not meant for the class. It is not going to only classify it. So they are going to learn the conditional, it is class conditional distribution. It is when a new data has been given, so I should know where it has to be placed. So based on the conditional distribution. So why am I going to use this probabilistic? Why we are going to use this probabilistic? So because the probabilistic model assumes the data comes from the underlying probability distribution. Okay, so this is the only correct value. So instead of me saying, oh, this is the only correct value, I can say the value is likely with probability of likelihood 0.8, and this value is likely with the probability of 0.2. So whichever is going to have the maximum value, that can be held. So this helps in this probabilistic method helps in identifying the uncertainty quantification. That is, when I'm going to get a data, if there is a missing data or there is uncertainty in the data, so I will be able to use this probabilistic method for prediction. So it will be helping me in the uncertain quantification, robust decision making. In the decision making, it will be helping out. And when I'm going to have a diverse outputs, and I'm having a diverse output, sampling of the diverse outputs can be, I'll be using it. I'll be able to use fill the missing values, or it can be used for avoiding the overfitting of the data. So what is the core idea behind this probabilistic generating model? So this probability generating model tried to learn probabilistic of theta, where theta are the model parameters. What are the model parameters given? It will be taking out that. And after training, we get a new data that is generating. It is going to generate a new X by sampling. So X is being X tends to P theta of X. So first thing is, it is going to generate the new X. I'll be able to get the new data by the sampling. Next, I'll be calculating the likelihood. So how likely is this sample? Okay, that is how you are going to estimate the likelihood. And then third one is you will be performing the inference from the likelihood. So how I'm going to infer? So how I'm going to compute the missing or the hidden variables. So for that, this probabilistic generative modeling will try to learn how to generate the new parameter using all the features or the parameters available, and it is going to estimate the likelihood of the data, and it is going to do the perform inference from the whatever the data you got. Okay, so here we are having out three types of models of probabilistic generative models. So first one is explicit density model, implicit density model, and the latent space. So here in the explicit density model, you will be classified with the whether it is fully specified likelihood model or whether it is deep explicit model. So fully specified likelihood model. So it is going to assume from the known distribution. Okay, assume a known form of the distribution, and it will be calculating the parameters. Okay, so more of likelihood models. So for example, in the naive Bayes, most of the methods they are using naive Bayes or hidden Markov models or the Gaussian models. So for this distribution, so the likelihood models is going to be identified. For the explicit models, so we'll be going for the normalizing the flow, learn an invertible transformation, how the invertible transformation is going to be done. So I wanted exact dog likelihood or bidirectional mapping, high resolution image generation. So for this, you'll be using a deep explicit models. So we are going to use a probabilistic generative model. So probability generating model, I said that we'll be having three categories. One is explicit, implicit, and the latent space. So in the explicit density model, we have to check whether the sampling or the data what we are having is going to be fully specified likelihood models or whether it belongs to the deep explicit model. Next is implicit. For the implicit density model, this is implicit means it is understood the term implicit means it is within. Explicit means externally we have to give that value. Implicit means from whatever existing I'll be able to calculate. We'll be able to generate the samples. Okay, for example, generative adversarial networks. So this will be using the implicit density model. From whatever the parameters or the samples I'm having, I'll be able to do it from there. Okay, so here the GAN will be used for whether it is going to be a generative or the discriminative case, whether the boundary has to be made or the new samplings has to be made, or whether it is extremely, if I wanted to generate the natural images, okay, from the input, whatever I'm giving out, from the input parameters, what are the features, whatever I'm giving out, so it has to generate a realistic image. Okay, the image, I'll be giving only the features. For that, it is going to generate the realistic image. Then I'll be able to use for when there is a instability of the data, or there is no likelihood estimation. So in that case, I'll be using out this implicit density model. So when I'm having a more of likelihood estimation, I can go for the explicit density model. Then the diffusion model. Diffusion model is so I'll be add noise to the data. Okay. So for the data, whatever the noise I'm having out, I should know how to reverse the noise. That is what diffusion. Diffusion means image diffusion or the voice diffusion, data diffusion. So to produce high quality images, so we'll be for images and the videos, we'll be using of this diffusion model. So for example, some AI tools like Midjourney, DALI, so that is image generation. So if I'm giving my old photo, if I'm going to give my grandparents' photo, which is going to be a black and white, okay, if it is going to be distorted also, that model using of this diffusion model, so I will be able to predict and I'll be getting a color picture, or so I'll be able to get the original, that is the image is going to be drawn. So that is going to be your diffusion model. So in the diffusion model, so where it is going to have the implicit parameters and the implicit data. So I'm giving an image, okay, that is not very clear. Okay, that is the input image, what I'm going to do, that is not very clear. So it is not going to generate or explicitly, it is not going to take any parameters. What it is going to do, if the forehead of the picture, if it is going to be damaged. So what it is going to do is, it is going to estimate from the given parameter, from the image, what it is going to check, and it will be finding out what pixels or what color has to be given. And using out that implicit data, it is going to build that model. It is going to predict what. So here, so it should be a forehead. If it is going to be this distance, it should be a hair. So what is the color of the hair? So it is going to take the data from the nearby and it is going to fill it out. So here, how it is going to be done is, it is going to add the Gaussian noise. The data Gaussian noise is going to be given, and you are going to again de-noise. Again, after adding out the noise, it is going to be reversed. That is, you are going to step by step to generate the samples. So that is going to be followed in the implicit density model. So next is going to be the latent variable model. So here latent itself understood that it is going to be a hidden variables, right? So the hidden variables are going to be taken off. So one of the very good example of the latent variable model is a VAE, that is variational autoencoders. So it is going to learn the latent representation, hidden values, and it is going to optimize with the variational inference. The variation inference like ELBO, it is going to optimize that work, and it is going to produce a smooth and smooth images. Okay, when we are going to compare it with the generative adversarial inputs. So these are some of the probabilistic generative model. And so I'll just again recap again. So why which model we are going to use? Okay, we should know which model or which data sampling we are going to use. That should be known. Whether we are going to use explicit density model, the explicit density model. So we'll be having our two methods. One is going to be the fully specified likelihood model. Okay, so we are going to assume from the distribution, parameters or the distribution. That is, we'll be estimating the parameter, what parameter is to be. Okay. Whereas in the deep explicit models, so we'll be normalizing the flow. Okay, the flow of samples will be normalized, and we are going to learn it from the transformation from one to the other. We'll be learning it. Whereas in the implicit density model, so we are not going to generate the samples. Okay. So whatever the existing one, so there we are going to do the implicit data. Okay. Here P of X explicit is not going to be done, and we are not going to generate the samples. Okay. The diffusion model. So as I was saying, so many of us must have used this model, that is for image generation. So when ChatGPT has come, so they have given for the image generation, DALI has been given. From then stable diffusion or the mid journey. Okay, most of us must have used this. Okay. Then latent variable. Latent means some hidden variables. So if I'm going to take any neural network, the neural network will be given input. So that will be taken by the neurons and it will be given to the hidden layers. So to the hidden layers, okay, some activity functions or modelings will be done and which is going to give to the output model. So in the output model, the output, whatever we are going to get the output, input, hidden layer and the output. So here in the output, so we are going to use this probabilistic methodology to get a generative models. Okay, so this is about the probabilistic generative model. So now we are going to see some of the, what are the key mathematical tools which will be used for generative model, probabilistic generative models. So here they'll be using the probability distribution. Okay, so whether it is going to be a normal distribution or Gaussian distribution, I have to find. So core concept which will be describing more of the likelihood, that is what kind of probability distribution, that is maximum likelihood estimation, MLE will be done. So here you will be finding the parameters theta to maximize the likelihood. So what is theta? Theta is going to be maximum of P of Xi. Okay. Next will be latent space. So latent space is the data, whatever I'm having, it is going to be represented in the lower dimensional data representation. Okay. If I'm having 3 clusters of data, so these 3 clusters of data, which is going to be represented in a 2D form, is it possible for me to represent in a single dimension? Okay, so in which axis it fits? Okay, how it is going to be? That is lower dimensional data representation, that is going to be the latent space. Okay. Next, likelihood, how the data is observed for the probability of the given model, and maximum likelihood estimation, that is parameter estimation by likelihood maximization, and the variational inference. So these are some of the mathematical tools we have to understand for using out this probabilistic generative model. Okay, so this is a neural network. In the neural network, so we are having a 3 input layer. We are having a 3 inputs. Okay, and this is going to be the hidden layer. I'll be getting this output. So in the supervised learning, so I'll be knowing out, I can check the output. Okay, so here again I'll be using the output layer. I can use the probabilistic generation generative, so that I'll be getting out the more optimized newly data can be sampled or new data can be generated. And the concept of probability. So I keep talking about the probability. So these are fundamental to machine learning and the data science. Okay, so while it is very easy to understand and model the single random variable in practice, but we don't end up with a single random variable. So we are being given with many random variables to interact with each other. So here we have given an example. So you can see that, so I'm having out 4 kind of sports, students, and what is the rating the students will be given is going to be the random variable. Okay, so you're having out multiple data. For this multiple data, so we have to form the random variables. Okay, so here in the random variable, the random, that is the probability. So we'll be having 3 types of probabilities. So that will be used for when we are going to use for the multiple random variable. When I'm having one, so I will not be ending up with one feature, isn't it? So in the last example, what we have taken, so that is, I have to identify whether the yellow ball has been given, whether that belongs to diabetic or non-diabetic. So only feature was given as glucose level. Okay. So there I had only one parameters. Based on that parameter, the classification has been made. But many of the in the real world, we will not be end up with one variable. So we'll be having on more than one random variable. So when I'm having more than one random variable, so how will I be able to use this probability? Okay, so basically we'll be having on three types of probability that is used for multiple random variables. So one is joint probability, marginal probability, and the conditional probability. Three probabilities are there. So what is the joint probability is? It is the probability of two or more events occurring together. Okay. So here, if I see, if I have the previous example, what we have taken. So the sports, student, and the rating. I'm having on sports, students, and the rating. So based on this, how this probability is going to be denoted. So it can be denoted probability of x is equal to a and y equal to b, or x is equal to a or y equal to b, or x is equal to a, y equal to b, and z is equal to c. So 5. Okay, so this can be given as a joint probability. So, but in the data science, when I'm going to, in the data science, the probability of observing an entire row of data, so which will denote a joint probability or joint probability over the multiple random variables. Okay. So I'll be taking a row, the data, the probability of observing the entire row when I'm going to observe. So it is going to denote a joint probability because we are going to take more than one random variables. So which is going to act over the multiple random variables. That is a joint probability. So marginal probability is going to be it is going to be the probability of specific value of one random variable for all outcomes of the other random variable. So what is going to be output of one variable? For example, it can be weather forecasting. So weather forecasting, whether I'll be getting rain or not tomorrow, that is going to be one random variable. So for that, I'll be using all other random variables. Okay, I should know what is the pressure, what is the temperature. Okay, so all these parameters has to be taken. Okay, so here it is going to be denoted by probability of x is equal to a for all outcomes of 1. So for this, for probability of x is equal to a and x is equal and y equal to b1. So you keep adding out all these things and to get the marginal probability. Okay, for instance, the probability of specific value of random variable that is going to represent the marginal probability. So here you are given with the two random variables, that is x and y we have been given. Okay, where for two subjects, English, Maths, and another variable y is going to specify whether it is male or female. Okay, so here if I'm going to take with the x, so what is the probability of English if you're going to take? It is going to be 0.1 plus 0.25. So here you can see probability of x is equal to English. So here probability of x is equal to English, and so you are taking another variable. So y, whether it is going to be male, y is equal to male, plus probability of x is equal to English, and that is x is English and y is a female, isn't it? So here probability of, that is the marginal probability here for when I'm going to calculate for the variable x. So you will be adding out 0.1 plus 0.25, which is going to be for the English. Similarly, we'll be doing it for the max. So for the max, you'll be taking out P of x is equal to max, y is equal to male, plus P of x is equal to max, plus y is equal to female. So you'll be getting 0.4 plus 0.25, which is going to be 0.65. But this probability value will be ranging from 0 to 1. So if you add this 2, you will be getting it to be 1. Okay. So if you are going to take for this P of y, male, Okay, for the male, if you're going to take, so again, you will be calculating with the whether it is going to be X is equal to English or X is equal to maths. So overall subjects for the male, what is the probability is going to be 0.5. The female is going to be 0.5. Okay, so this is how the probability of the specific value of the random variable is going to be represented. So using the marginal probability. Okay, so for the probability of a specific value of one random variable. So I think I'm making it clear for one random variable, so which is going to be X, for all outcomes of another random variable of Y. So here, X is the subject, what has been, so if I wanted to calculate what is the probability of specific value for English means, I'll be taking out the other variable Y, which is going to be male and the female. So for the given condition, for the given example. Okay. So first one is the joint probability. The joint probability, so you will be having the probability of two or more events occurring together. Okay, everything occurring together will be taking out that, which is going to be denoted as P of X is equal to A and Y equal to B and Z is equal to C. Okay, so whereas in the marginal probability, so to find the probability of a specific value of one random variable, so I will be finding out all the outcomes of the another random variable that is your marginal probability. Next is the conditional probability. So the conditional probability of the event will be given with the other event. Okay. So if I'm performing cricket very well, okay, so all the students are performing very well. This sports, if you're going to take, so how which sports is performed very well. So I'll be taking out all the probability of all the sports and then the ratings will be taken and based on that only it is going to be calculated. Okay. So here it is denoted as P, okay, P of X given Y. Okay, so I'm going to calculate X for the given Y. Okay, so for that conditional probability will be, so P of X is equal to A given Y equal to B1. So you will be getting out the conditional probability of P of X is equal to A and Y equal to B1 divided by P of Y equal to B1. So here in this given example, so I'm getting the conditional probability of the student, okay, student A for the sports cricket. So here I will be taking out the student, that is that row will be considered. Okay, the row student A and the rating has been given 5 for the student who is going to play cricket and P of cricket. P of sports is equal to cricket. So how it is going to be calculated using the conditional probability. Okay. Now this predictive modeling, it is primarily centered around the conditional probability. So where we estimate the conditional probability for the output given as an input. For the output given as an input for the output. So we are going to do the predictive modeling. And most of the, as I said, in the neural network, so I can show you. So in the neural network, so these are the hidden layer. For the hidden layer, so whatever the output, when I'm going to get the output here, okay, the output when I'm going to get, I'll be using the probabilistic modeling to generate the data set. Okay, so this is some of the key concepts. So what we have to know about the joint, when you'll be using of the joint, marginal and the conditional probabilities. And most of the time we'll be using this conditional probability based on the input. So now, so when dealing the multiple random variables, all these things, why? Because this probability is when we are going to deal with the multiple random variables. So joint probability is probability of events A and B occurring together. When these two occurs together, I'll be getting out this event. Marginal probability is probability of an event X is equal to A. So I'll be calculating irrespective of the another random variable. Conditional probability is probability of an event A given for the event B. Okay. The generative models learns the what type of underlying distribution, and they can generate the new samples. Okay, so if you're going to see P of y for the given x, okay, so you will be using all these sample points. Okay, you will be learning it from the data and use this from the sample points. So, however, this is not possible with the discriminative models. Okay, this cannot be done with the discriminative model, because in the discriminative models will be only will be finding out the boundary class, boundary line. So here, if you're going to see a generative model, it will be possessing the discriminative properties, and they can be used for the classification task. Okay, so here, generative model possesses the discriminative properties, but discriminative properties do not, because they will be doing only the classification. So they will not be able to generate the new samples, new data sets cannot be generated. Okay, so this is another example. So just imagine yourself as a language classification system. Okay, so language, so you're going to classify the language and you're going to predict the language. So there are two ways you can classify the languages. One is, I can learn every language and then classify a new language based on the acquired knowledge. Based on the acquired knowledge, I'll be classifying it as a new language. Or I can understand some distinct patterns in each language without truly learning. I'll not be learning the language. So, for example, if it is going to be a Telugu means, so if it is going to end with lu means, I can say it is a Telugu. Okay, for Kannada, I'll be having got one method. For Marathi, I can have one method. So, with the endings, I'll be able to classify this is a Marathi, this is a Telugu, and like that. So, how can we, so for the given problem, this is a given problem, how can you figure out which of the above is going to be a generative and which is going to be a discriminative? So I'll repeat it. So we are going to imagine ourselves as a language classification system. Okay, this is the language you're going to learn and you're going to predict that language. So what are the ways of predicting the languages? One is, I have to learn all the language. So if it is going to be South Indian language, so I'll be having out all the South Indian language. I will learn it and then I'll be classify. I can classify a new language. So based on whatever the knowledge I have acquired. If it is going to be in Greek, if I'm going to speak, I'll be able to classify this is going to be based on the languages what I have learned. Okay, or else I can understand the patterns. As I said, I can understand the patterns of each language, but I don't know. I might have not learned the language, but based on some prediction, I'll be able to do it. Okay. So now I wanted to check whether which one is going to be a generative and which one is going to be a discriminative. So here, if you're going to see, learn every language and then classify a new language based on the acquired knowledge. Okay, so this is going to be the generative model or generative, because we have learned the underlying distribution of each language. So these are the words, this is a grammar. So everything we have learned, underlying distribution of each language is learned. And if other words you learn, that is going to be a joint distribution, which is going to be probability of words, okay, whatever the words I'm having and the language. Okay, now if you are going to have a generative, okay, that is you, if it is going to be generative, you understand the underlying distribution of the language. So this, I can say it is like a normal distribution. You can understand what is the underlying distribution. Now you can generate the new sentences. Am I right? So you'll be able to generate a new language or new sentences can be generated. So this is going to be a generative. So first, the second approach, what I told is, just you'll be understanding the pattern. Based on the pattern, you are going to classify. So the second approach is going to be the discriminative approach. So this is because you only learn specific distinctive patterns of each language. Okay, Tamil, okay, or Telugu means, so most of the time, if it is going to end, if the word, if I'm going to check, if it is going to end with two, okay, if it is going to be Kannada, this is going to have this pattern. So I'll be understanding only the pattern, but I don't know the true meaning of that language or the words I'll not be knowing of. Okay, so what it will do is, so words appear, it is likely to the language. It is going to be like the language. Okay, if the specific set, it is like language Telugu, it is like the language Tamil. So we'll be finding out the patterns. Okay, if this specific set of words appear, it is likely to be the language. So that I'll be classifying it like this. So what you're going to do is, you will be forming all the clusters. Okay, you learn the conditional distribution based on the language for the given words. For the given words, you are going to identify the language. Okay, this word, it is with Lu. Okay, so it is going to be of Telugu. Okay, or if this is with Ru, this is going to be of likely with the language of Kannada. So for the given words, so you are going to identify the language. So here you are not going to generate any new language, we are only classifying it. Okay, so can you generate new sentences here? Will I be able to generate new sentences here? No. So here we are only classifying it. So we are only making out to which it belongs. Okay, so this is going to be the discriminative model. Okay. So again, so you are going to learn every language and then classify the new language, or understand the patterns and truly learning the language. Okay, so this is a example I wanted to talk about the generative and the discriminative models. So again, a summary of this two models. The above description would have told you that generative models are more generally useful, but this is because generative models have their own modeling complications. Mostly they'll be using out this probabilistic method to generate. Generative models require more data than the discriminative models. Then it will relate it to the language classification. Then you will be able to imagine amount of data you need to learn all languages in the generative approach, or the amount of data you need to understand some distinguished patterns, whether it is a discriminative approach. So if you're going to take, because generative model will take long time for the modeling. So in the above example, what we have taken is discriminative model outperform generative model in the. So when you're going to take the classification, I think discriminative model good, sounds good. So this again we have said. So it is going to be the class of machine learning model that learn the underlying probability. So I keep telling out. So they are based on the probability distribution of data, which can generate the new samples. Okay. So generative model, it is going to use a joint probability distribution. Okay. Types of generative models. Variational autoencoders. Okay, so which is going to give you the smooth data transitions and the latent space exploration. Then GAN, that is generative adversarial network. It will be having out, so all what we are following now, so that is two neural network and a generator, and it is going to compete with each other. Generator tries to create a realistic data samples, with the discriminator tries to distinguish between the real and the generated. That is, now we are having so many things, right? Fake news, whether it is fake image. Okay, now people are generating this using of the generative model. The human being who are not there in this world also, it has been generated, isn't it? Then auto-regressive model, so which is going to predict the next data point based on the previous points. Okay, so which is going to be like a transformers, RNN. Okay, so this, today it is raining. Will it rain tomorrow? Okay, so that is going to be which is going to predict based on the temporal data, it is going to predict the weather. Then flow-based model, so which is going to be used in the series of transformation to map the data to a simple distribution. So like your Gaussian distribution. Okay, so this is going to be very effective for mapping data for the simple distribution. Okay. So this is going to be these are the types of generative model. So I will not say every type. So these are the types of the generative models. So I have taken one example, that is auto regression model. The auto regression model, it is going to predict the probability distribution of each element in a sequence, leveraging the information from the previous element. Okay, so this auto-regressive models are very well known for their interpretability, very flexible, and capacity to capture the temporal dependencies, or like time series data. We'll be taking time series, natural language, or speech, which is going to be used in this various domain like time series data or clinical data. So for this, they'll be used. It is very interpretability. I can easily interpret, and it is very flexible and capacity to capture this dependency. That is, temporal dependencies can be classified. So this model uses and predicts the probability distribution of each element in a sequence, leveraging the information from the previous segments. So based on the RNN, that is recurrent neural network or the transformer model, so these language models have demonstrated the state-of-art performance in tasks like text generation and the machine translation. This, your ChatGPT is a quite good example for a transformer model. So how this is going done? The model performance depends on the appropriate selection of the order of probability and the choice function. If x depends to y, if this is going to be the relationship between the variables is going to be given with the function f. Okay, and the selection of order, and this is going to give you the model's performance. Okay, the model performance depends on the appropriate selection of the order and the choice of the function. Okay, so one common approach of training these models, it will be using the MLE, that is maximum likelihood estimation, to observe the data given in the model parameters. So if you're going to take the optimal model parameters, so which is going to maximize the likelihood function. So here, training this model is using the minimum likelihood estimation, which will be helping to observe the data given by the model parameters. But optimal model parameters are those that maximize the likelihood function. This is going to be the auto-regressive application, model application. So as I said, so which can be used for the time series forecasting. So which will be used for predicting the future values in time series data. So which is going to make very valuable in the share market, the financial forecasting. It will help auto-regressive model, the weather prediction, okay, in the weather prediction, and in the demand forecasting. Okay, time series model, it is finding out a very extensive application in the many fields ranging from sales, share market, weather forecasting. So which is going to give a versatile and uncertainties is going to be, what are the uncertainty is going to be predicted, the future prediction is going to be done. So if you're going to take, I think 2 decades back, or okay, I'll take 2 decades back. So everyone of us knows that. So when the weather forecasting was very, very poor, they'll be saying everyone must have not this rainy days, no one would have forgotten Ramanan, the weather forecasting. So when that person comes, we'll be very happy because he'll be saying, God, because of heavy rain, tomorrow it will be a holiday for schools. Right? But what was the weather condition was? So the next day we'll be having a warm sunshine. Okay, but we'll be enjoying the holiday. So that was the case. It was 2 decades back, it was like that. The weather forecasting was so, it was not very perfect. Okay, now with the advancement of all this data analytics and how this models has been working out, that is especially, for example, of the autoregressive model, so we are able to accurately, we are able to predict, this is what is the climate. So this is how much rainfall you'll be getting out. So where the tide, what is the size of your tide, everything we are able to predict. And very easily we are able to say accurately, okay, it is accurately you are able to predict and say everything. Okay, so that is the time series model. So now what we are having is, we are able to tackle the uncertainties, what is there in the future prediction. So this also plays a major role in the share marketing, mostly in the financial forecasting. This model is helping a lot. Okay. So when faced with the uncertainty, so using out this time series model, it is becoming very effective approach for the accurate forecasting. Okay. So this is one of the application where we are using this autoregressive model. So the natural language processing. So many translators we are using out. Language modeling is very common application. So which will be enabling the prediction of the next word in a sentence. So based on the preceding words. So what is, so I like to go, if I'm going to give, what is the next sentence? When you're going to type itself, you will be getting out and you will be getting out so many recommendations of the sentence. That is what is the next word in the sentence. Based on the context, based on the preceding words, you are able to get this. Okay, this capability facilitates tasks like text generation and the machine translation. So do you think that that is the generative AI is very new concept? So can anyone tell, so when the Google Translator, when we started using this Google Translator? So Google Translator, we had it in 2006. 2006, yes, into Google Translator. And this NLP process also, we have been using it from 2010, 11, we have been using it. So all this are the evolutions of what the model we are saying it today. Okay, so yeah, what the ChatGPT, Gemini, so all these things are using of this regressive model. That is natural language, that is prediction of next word. Prediction of next word. Okay. The speech recognition. So another important application is the speech recognition. So they have been used to model the correlation between the adjacent phonemes and the acoustic features. So based on the phonemes, they will be using of this or the voice features. We'll be able to do the speech recognition. Next, audio processing. Okay, these audio processing are employed for tasks such as speech synthesis, the removing the noise, denoising, and the audio compression. We have been using of. And there are so many applications of the that is autoregressive model. And in the time series, I have mentioned very few. And we are having out supply chain forecasting is a inventory forecasting, then product sold for, what is the product sale forecasting, or epidemic or pandemic forecasting. So all these things are based on this time series forecasting. So these are some of the application of the autoregressive models. Then in the probabilistic generative model, which is going to use the probability distribution of the data. For the given data, the probability distribution is going to be. What is the main objective is to capture the relationship between the features. What are the input features I'm having on and target labels while explicitly modeling the uncertainty in the data. You can underline uncertainty in the data. Okay. The main objective of the probabilistic generative model is to capture the relationship between the what are the input features I'm giving and target labels while explicitly modeling the uncertainty of the data. This is the core objective. So at the core of this models lies the concept of probability distribution, so which helps us to understand how the input data is generated by the probabilistic standpoint, as well as we'll be able to estimate the joint probability distribution of the input features and the target labels, which will allow us for getting out more comprehensive understanding of the data generation process. So how your transformer is going to work. The learning process involves estimating the model parameter that best fit the observed data. Whatever the observed data we are having, it has to do the best fit. So here common techniques of the parameter estimation will be using it to be a maximum likelihood estimation and the Bayesian inference. Okay, so they offer a broad spectrum of applications. So one is your image generation. Models like variational autoencoders, GAN, can generate new images by sampling from the learned probability distribution, enabling the realistic image synthesis, and it is going to do a very beautiful content generation. Creative content generation is also being done. Okay, so in the in this context, if I'm going to talk about the variational autoencoders, so it has been designed with the encoder that maps the data into the latent space. That is a hidden layer, the hidden data to the latent space, while the decoder generates a new points from the samples in that space. So here I've given this diagram from the latent space. The generator, it is going to generate samples, it is going to be taken. That is generated samples with the real samples. So this is going to be given to the discriminator. This discriminator is going to make a decision. And this keeps in a loop. Okay. So here, VAE, that is variation autoencoder, is designed with the encoder. That is this encoder, what it does is it maps data into the latent space. From the latent space, the decoder generates a new data from the samples in the space. Then collaborative filtering, that is recommendation system, a very good method. What is used today for all the online shopping, they are using out the recommendations system can predict user preference by modeling the probability distribution of user and the item, what is the interaction they are having on. So which is going to give you the personalized recommendation. That is going to be one of the probabilistic generative model which is used for the collaborative filtering. Then anomaly detection. Any anomaly is there. In the data can be detected by comparing the likelihood of the new samples. And mostly this anomaly detection, this probabilistic generative model is used for the cyber security in today's world. That is, if there is any new data logins, okay, any log files, if there is any deviation in the log files, all these things can be predicted. That is unusual data points that deviate significantly from the model's distribution. So they will be flagged as a anomaly. So it is very easy to identify the anomaly, which is widely used in many applications, this anomaly detection. That is, the probabilistic generating model is used for this. And one of the applications is going to be the anomaly detection. So here is one example. A company wants to generate high quality and realistic images of different types of flowers to use it in its e-commerce platform. Okay, we wanted to generate. However, they have limited data set of flower images and they wanted to generate new images to expand their inventory. Okay, sometimes we also see, isn't it, some images, so which is not realistic also, they'll be putting it in the e-commerce platform. Okay, it is going to be given for the so there are so many fake images also available, but how to find out whether it is a real image or fake images? Again, that is going to be another research area. So here, the variational autoencoders. So as I said, the variational autoencoders. So they have an encoder, then the decoder, and they are learning a compact, that is a latent space for representation of the real images. So now, so the problem given here is, I wanted a high quality real, which is going to be more of realistic images. I wanted to display in my e-commerce website. Okay, I'm going to sell flowers in the e-commerce platform. So now when I'm going to see the data set, what I'm having is very, very minimal. Okay, so but now I wanted to generate the new images. Okay, so for this, I'm going to use this variational autoencoders. Okay, now the existing images, it is going to generate new images. Okay, so this model, for instance, is trained with the reconstruction laws, and there is a method called Kullback-Leibler divergence to ensure accurate image generation and the smooth latent space should be there. Okay. By sampling from the learned latent space, the VAE, that is variational autoencoder, generates diverse and realistic flower images, allowing the company to expand its inventory and improve the user experience on this platform. This model enable efficient and creative data generation for various business applications. Okay, this is one of the example what I have taken where we are going to use this probabilistic generative model. Okay, so what are the key capabilities of the generative models? Okay, so they will be used for data generation. The primary capability of generated model is to generate new data samples and that resemble the training data. So this can be useful for creating synthetic data for training other machine learning models, generating realistic images and videos, and creating new content such as text and music. So if you're going to take in the medical field, so we are not given with all the live samples, or we'll be limited with the samples what we are getting it out, right? So in that case, we can go for creating the synthetic data. So based on the real data, I'll be able to create the synthetic data, which can be used for the research purpose, or which can be used for the machine learning models. Data augmentation. Generative models can be used to augment existing data set by generating new samples that are similar to the original data. Okay, again, this can help in the machine learning model. So when the training data is going to be a limited one. And for the language representation or representation learning, generative models can learn useful representation of data, which can be used for the machine learning task. Okay, so all these things, again, a data compression. So this can be used. These are the key capabilities of the generative models. So you can see what are the diverse applications of the generative models, which can be used for image and video generations. So many of us might have used that is AI tool to generate the images. Our photos can be converted as a video. Okay, so you can use it for storytelling, animated movies. So all these things can be done using the video, image and the video generation. So using this model, generative models. Okay, text synthesis of text. and music composition, which can compose new music in a variety of styles. Okay. And drug discovery. Generative model can be used to generate new molecules with the desired property, which can accelerate the drug discovery process. Again, this is again a very big research area where many researchers are going on with a personalized medicine. Okay. So everyone will not be given the same medicine. So each and everyone has to be tested, and everyone will be given the personalized medicine. So that is the new drug from the existing disease, from the existing molecule. So how the new drug can be designed. Then medical imaging, which can be used for generating the realistic medical images. So which can be used, these images can be used for training the medical professionals and developing the new diagnostic tools. For the fashion design, for the art generation. So for this, we'll be using of this generative models. What can probabilistic generative models do? So it can create more realistic images. So again, the same drug or the molecule generation, financial forecasting, low likelihood events, which is going to be anomaly detection, missing data imputations, stimulating physical systems. So these are the probabilistic modeling can be done. So enhance creativity by providing new tools. So it is going to provide a new tools and inspiration for the creativity. For the accelerated scientific discovery. So scientific discovery through the hypothesis generations and the data analysis can be made. Automation of content creation. We can go for content creation so that freeing the human creators for strategic tasks. Okay, they can do some important tasks. Personalized experience. So for this probabilistic generating models can be used. So the summary with the models, the Gaussian mixture model, it is going to compute the probability of X, but it is not going to use the latent space. So it is going to be like a clustering. And the variational autoencoders, it is going to approximate the value of P of X. It is going to use a latent space. So the VAE can be used for representation learning. For normalizing flows, it is going to go for the density estimation. This probability density estimation. Then adversarial networks for the photorealistic image generation, and the diffusion model will be used for the SOTA image and the video generation. So which is going to implicitly compute the P of X, but it is going to use a latent space. So this is about the probabilistic generation model. Okay. So we'll see what are the challenges and limitations we'll be following. They also follow several challenges and the limitations. The training complexity. Okay, that is training generative models can be computationally expensive, and it requires a large amount of data because it has to predict what is going to be the next. Next, it can go for mode collapse. GAN can suffer from mode collapse where the generator only learns to generate a limited set of data samples. And the metrics, whatever we are evaluating, the quality of generated data can be challenging, as there is no single metric that can capture all aspects of realism and the diversity. As I was saying, the example what we have seen, that inventory, that is a flower, they wanted to have so many flowers on the e-commerce website. So they are using of this to generate the flowers. Okay. Sometimes, which is not existing in this world, also it can generate from the input, whatever you are going to do. So we don't have a metric to identify whether it is of the reality can be identified. Okay. I think a few days back also we have been seeing out like Nirmala Sitharaman saying out the crowd that you deposit today 22,000 and after every month you will be getting out this money. So it was a fake news. But as Nirmala Sitharaman is saying out, the fake, it was being given in all the social medias. Okay, and the Sundar Pichai, he was supporting it. I think how many of you seen? I don't know. I think 22,000 if you're going to deposit today, every month you'll be getting out this month, this amount of money. And after so many years, you will be getting some crores of money. Okay, that was advertisement given. As so, Nirmala Sitharaman, directly she is speaking, and Sundar Pichai is also supporting that. So these are something which is going to be generated using the generative models. But so how it is going to capture all the aspects of the reality. Okay, then there is something called what we have to consider as ethical concerns. Okay. Generative models can be used to create the fake news, deep fakes, and many malicious content, which is going to raise the ethical concerns about how this is going to be misused. That is potential misuse of this content. So that's all about the generative AI. Next next topic is going to be the latent spaces and distribution. So latent space, latent itself is going to be a hidden. Okay, so it is going to be a hidden, and which is going to be that is decrease the dimension. Okay, the dimension is going to be decreased. That is representation of the data. That is low dimension representation of the data is going to be done, and the mapping is going to be done in the VAC, that is autoencoders. It will be using the latent space. That latent data will be mapped, and then it is going to be given to the deep. Okay. So let's see what is the latent space. So as we have been looking out into this model like autoencoders, GAN, transformer models. Okay, so these models learns pattern in form of a data. It represents those data in a low dimensional space. Okay, it is going to represent it in a low dimensional space. So for example, so if my image size is going to be 1024 into 1024 into 3. Okay, so if I'm going to have some 3 million numbers, the latent vector can be given as a low dimensional space with 128 numbers. Okay, so this latent vector, it will help us to capture the style, the shape, the pose, the color, the structure, okay, which is going to be in a compressed internal representation, which is going to be a latent space. So here in this example, if you're going to see, so add a new cluster in the latent space, that is the encoder, so that when it is decoded, you will be getting out this image. So in the realm of generative AI, what is a latent space? It is nothing but a multi-dimensional vector space that represents a compressed and the abstract encoding of data that a generative model can be trained on. So just you can think about, so the neural network I have seen, here I have given, we are having an encoder. So the bottleneck, so the bottleneck, what we are having here is how the latent space is represented and how again it is going to be reconstructed as an image. Encoder, the real bottleneck is going to be the latent space representation and the decoder. Okay, so now think about this hidden layer or the low level representation of the original. That is often it is going to be a high dimensional data. Each point in the latent space corresponds to the specific set of features or characteristic which is going to be learned from the training data. Okay, so for example, let us imagine that you are having a collection of images of faces, so many faces you are having on. Instead of storing each image as a large array of pixel value, a generative model learns to represent each space as a point in the latent space. So if my face has to be, or some 1,000 faces are going to be stored. Okay, so instead of storing it as a array of pixel value, so I will be giving it as a point. Okay, with a point and the mapping is going to be done. So this point, what it does is it encodes the essential features of faces, such that essential features of faces, it can be the shape of the eye, color of the eyeball, okay, the size of the nose, and the color of the hair. So these features on the faces can be, it can encode and it can give. And how it is going to be represented. So here, latent spaces are fundamental to the functionality and which is going to be very effective for the generative AI model for the several key reasons. So 5 key reasons I have taken here. One is the dimensionality reduction. This latent space provides a way to reduce the dimension of the complex data. Okay, so my face, that is the image of a face which is going to be stored in a large vector, it can be stored with a few points. That is with the mapping of high dimension data to the low dimension latent space. So now this generative models can learn more efficiently and avoid the curse of the dimensionality. Okay, so that is the dimensionality is reduced. Data generation. The primary, that is the more primary purpose of the latent space is to enable the generation of the new data samples. By sampling points from the data sample and decoding them back into the original data space, generative models can create the novel data which is going to resemble the training data. And another important feature is going to be the data interpolation and the manipulation. Okay, as we need a smooth interpolation between the different data points, latent space will allow this smooth interpolation. Okay, by traversing the latent space, so it is possible for us to generate the continuous sequence of data samples and that gradually the transit from one point to the other, from one data point to the another point. The transition should happen in a very smooth way. So this enables interesting applications. What are the applications we can do with this transition of these points? So we can go for morphing of images, or creating very smooth animations. There will be no noise, no noise or disturbance will be there in the morphing of images. Furthermore, this can be used for manipulating specific dimension of the latent space, which can allow for the controlled modifications of the generated data. So for example, in the face generation model, changing the specific dimension might alter the age or gender of the generated face. Have you ever seen this? So when I'm going to do the face generation model, some dimensions, if you're going to change, if you're going to alter the change, or it can change the age. So you might be saying if someone is adding, so I don't know what they say, hair addition or something they say, isn't it? When they're going to add some hair, a bald hair, when the hair is added, the age will be, so they can look very young, right? And the gender can be changed. Okay, so this is how the manipulating the specific dimension of the latent space can allow the controlled modification of the generated data. Next is data disentanglement. Okay, it is the well-structured latent space should disentangle the underlying factors of variation in the data. So whatever the variations you are going to have in the data, it should be. So what does it mean is, that is each dimension of the latent space should correspond to the specific independent features of the data. So this entanglement make it easier to control and manipulate the generated data. Okay, and the regularization, the latent space acts as a regularizer, so preventing the model from simply memorizing the training data. Instead of memorizing the training data, it will be allowing, or it will force the model to learn the compression representation of the data, and the latent space encourage the model to generalize better to the unseen data. Okay, so these are 5 fundamental functionality, so which is going to make generative AI, which is going to give you generative AI, making it as a key reasons. That is a latent space. That is the latent space, the dimension, which is going to reduce the dimension. That is the dimension reduction is done, data generation is done, data interpolation and the manipulations of the data has been done. Okay, data disentanglement. Okay, so this is one of the feature of the latent space, and the regularization. Okay, so using this, the latent spaces plays a fundamental to the functionality of the effectiveness of the generative AI models. So why do we need? What is the need for the latent space? Why do we need this latent space? This latent space allows AI model to understand and get the reasons about the data. Okay, whether it can group similar sentences, or it can group the similar story content. Okay, all these stories are similar. Or if I wanted to identify the similar faces. Okay, so this understand and reason about the data. There is another AI called explainable AI. So it gives the reason. Here, you're going to understand and give the reasons about the data, how the similarity is being done. Okay, next is it can generate the new realistic data. Okay, synthetic data. It can be generated. So which is going to look same like your real futuristic data. Like it can generate text, it can generate images, videos, music, everything can be done. Okay, then it can modify the content. Okay, using the LAT, because it's a mapping what we are doing, isn't it? So you can modify the content using you can change the face expression. You can rotate the object, or you can even change the meaning of the sentence. So the modification of the content can be done, and you will be able to do the interpolation. That is, I can blend 2 images or 2 styles. The blending can be done using of these latent spaces. So as we have been talking about how we are going to generate the new AI or generative AI. So here we are in need of the hidden layer is going to be the latent space, which will help to perform all these things. That is, similarity can be found, whether it can generate a new realistic data, it can modify the content, it can blend the 2 images or 2 styles. Okay, so for this, we need this latent spaces. Okay, one of the example is intuition. Suppose you train a generative model on faces. Okay, generative model on the faces. The model might learn that latent, so points will be given, right? So for the dimension 1, it is going to give you a hair color. Dimension 2, what is the smile intensity of the face? Dimension 3, I can take it as a face angle. Dimension 4, it can be gender expressions. Okay. If it is a male having a mustache, all these things are going to be given. And dimension 5, it can be like a age-like features. Okay, so these are the model might learn. Okay, with the dimensions. So these are not manually programmed. This model discovers them automatically. This is how the latent space is going to be given. Okay, latent 1 means it is going to give you the hair color. So if I'm going to modify this hair color, so I will be having the image is going to be modified. Okay. Then this underlying mathematics. What is the underlying mathematics of the latent space visualization? So we are having out 3 methods. That is dimensionality reduction technique. So we have to go for the dimension should be reduced. So for this, I have taken one example. So here you are able to see. So imagine we have gathered data on the height, weight of some 1,000 people has been taken. And now if I'm going to plot this on a 2D graph, so you will be able to observe how it is distributed. Okay, so here we are able to see how these data is being distributed. So with the height and the weight, the distribution has been made. And additionally, so if I wanted to normalize the data to the range of 0 to 1, okay. So if I wanted to make it as a normalize the data from 0 to 1, so my graph will be having from 0 to 1, 0 to 1. So now, so this is how you'll be able to see the data, which is going to be represented in two main directions. So here, so what is the so here how this data has been, so you can see this points, isn't it, points? And here the two arrow marks has been given, one is the red and the green. Okay. You can see the data varies along the two direction represented by the green and the red arrows, and the variation along the red arrow seems to be more significant than the green arrow. Okay, than the green arrow, you're able to see this, the data distribution. So these direction in which I have to follow will be taking the dimensionality reduction techniques, which will be termed as a PCA, principal components or principal component analysis. Okay, so here I will give one more example. So what is this principal component analysis? So it is going to find the principal components of the data set. So this principal components, which is going to be orthogonal, they can be uncorrelated, but we have to capture the maximum variance in the data. That is covariance. We'll be terming it as a covariance. What is the covariance of the data is going to be identified. So PCA projects the data onto a lower, that is, it is one of the dimensional reduction. So we are going to, what is the latent space? Latent space is nothing but dimension. We are going to reduce the dimension, isn't it? Wow. So PCA is one of the method for the dimensionality reduction technique. So here what it does is, it projects the data onto the lower dimensional subspace defined by the principal components. So effectively reducing the number of variables while retaining the same original variance as possible. So if you are able to see here, so I have taken the height and weight of your people. So when this is going to be reduced, so we are able to see this red arrow. The red arrow seems to be more significant than the green arrow. Okay, so here we are going to select this red color for applying the principal component analysis. So I'll give one more. This is the example. Another example. So for the data set with the cholesterol and the blood pressure. So if you are having so here three clusters has been formulated. So you're able to see the three clusters with the blue, red, and the green. Three clusters has been formulated for the data sets of cholesterol. It can be low cholesterol, low blood pressure, or high cholesterol, low blood pressure. So form some three clusters from the data sets has been formed. So when I wanted to reduce this dimensionality, so when I'm going to reduce it as single direction, so what happens is I cannot retain, because this green and red will be overlapping. When I wanted to get the originality, I'll not be able to get the original data. But here you were able to see this PCA with this arrow mark. So this I'm going to reduce in this given with the arrow mark. So you can see these clusters of data, which is going to be reduced in this pattern. Okay, in the figure what has been given, it has been reduced in this pattern, and which can be regained with the originality. Okay, which can be, so that is what is PCA projects the data onto the lower dimensional subspace, okay, which is going to be defined by the components. We'll be talking about these principal components and reducing the number of variables while retraining. So when I wanted to get back, I'll be getting the original variance. Okay, so here, so this is a 3 clusters. So if that is a 3 clusters of data sets what I have taken. So if I'm going to reduce it either in the x-axis or y-axis, if I'm going to reduce into x-axis, this red and the green is going to merge. If it is going to be on y-axis, this blue and red is going to merge. So when I wanted to get back, it is not possible for me to get back. So you can see in this diagram. Okay, so I'll not be able to get back the original. Okay, so using this PCA, so what I'll be doing is I'll be calculating the covariance, and based on the covariance, this has been given. So I can now reduce it to the x or y, and I'll be able to regain it again. Okay, so here you can see. So if I wanted to represent this data on a single axis, so you are going to project, one way to do is to project the data onto the largest principal component, which is having the largest principal component. Okay, and so this is how you are going to get the original horizontal axis. Then how it is going to work? It is PCA. So you just have this in your, so this sample example you just keep, that is height, weight, how it has been represented in a graph, and how this PCA is going to function. So I said only arrow mark has been given, how this PCA is going to work mathematically. So this is going to be standardized. The data is typically standardized. Okay, where we are going to take the mean center and scale to the unit variance to ensure the variables with a larger scale do not dominate the analysis. First is standardization. Next, you'll be finding the covariance matrix. The covariance matrix of the standard data is computed. Okay, then you'll be going with the eigenvalue decomposition. The eigenvectors. So from the eigenvectors and eigenvalues of the covariance matrices, when it is going calculated, so this itself will give you the amount of variance explained by the principal component. What is the variance you will be? Based on that, you will be selecting whichever is going to have the maximum value, that vector value will be selecting for the principal components. Okay, and then it will be projected. Excuse me, anyone raised your hands?
Ma'am? Yes, you stand.
I've seen someone raising their hands. No. Okay, another 5 minutes, I'll finish it. So this, I have taken it from principal component analysis, how it is going to be done. Okay, so first the data set matrix. Okay, x is equal to x1, all the features, x1 and y1 will be calculating. Then the mean is going to be calculated. That is x1 plus x2 plus x3 divided by n, and the y variance will be calculating for the given data set. And then the data is going to be centered. The data is centered. x1, whatever the mean, what you are going to calculate, x1 minus x dash, x2, that is the centered value will be calculating. So from this, the covariance matrix has been identified. Covariance C is equal to 1 by n minus 1 x to the power of t into x. Okay, that is the transpose of this matrix. Then the covariance matrix, from this will be converting into the eigenvectors. So here, I think you can take any one data set and you will be able to do this. After this eigenvector has been calculated, this is going to do the projection. Okay, strength and weakness of this PCA. So it is very simple and it is computationally effective and relatively easy to implement. The variance maximization has been made in the principal components, which is going to capture the maximum possible variance of the data. There is a linearity and the interpretability of this component. The weakness is the linearity assumption. It is going to assume the linearity. That is, the data lies only in the linear subspace. It may not perform well on the data with the non-linear. When there is a non-linear relationship, this model or this doesn't work out well. And it will be having out the problem with the outlier. When the data what has been collected, when it is very sensitive to the outlier, they cannot significantly influence the covariance matrix. That is, the values will be drastically changing, and the prediction will be wrong. Then the loss of information, and that it is very difficult with the Gaussian data. It is very easy to do. It is very effective, but for the non-Gaussian data, it doesn't work well. It is a weakness of the PCA method. And this is the complexity order of n into b squared plus d cube. That is the number of samples and the number of features what we are having on. So this what is the complexity of this algorithm. Okay. Next method is t-distributed stochastic neighbor embedding. Again, this is another that is dimensionality reduction, which is used for the non-linear technique. Okay, so this will be suited well for visualizing high dimensional data in the low dimension. Okay, where you'll be using out this stochastic neighbor embedding is where we have to preserve the local structure of the data. That is, we are going to points that are very close together in a high dimensional space are also close together in the low dimensional embedding. Low dimension embedding. Okay. So for example, if I'm taking an image, so if I'm going to take image a part, okay, so here the pixel x1, y1, I'll be having out more probability of the same color, x2, y2, and slowly it may fade. So how this stochastic neighbor embedding. So neighbor embedding is where in the high dimensional space, if the points are very close, it is also possible in the low dimensional embeddings. Okay. So what it does is, it is going to do the pairwise similarity in the high dimension. Okay, pairwise dimension. In the high dimension, the pairing will be done, which is going to be followed to the low dimension. Pairwise similarities first in the high dimension, pairwise similarities in the low dimension. Okay, and then it is going to do the minimizing the Kullback divergence. Okay, the main goal of this SNE is to find the low dimension embedding that minimize the Kullback divergence. So because between the pairwise similarity distribution in the high dimension and the low dimension. Okay, so it will be used for the optimization. The use cases of this is we can use it for the data visualization, visualizing high dimensional data like image or text data, etc. Then for the cluster analysis and for the exploratory data analysis, this SNE is used. Uniform manifold approximation and the projection. That is UMAP. UMAP is a non-linear dimensionality technique that aims to preserve both the local and the global structure of the data. So which is considered to be a very faster and more versatile alternative for this. How this is going to work is, again, it works on the fuzzy complex method, fuzzy simplical complex. So first it constructs the fuzzy complex representing the data's manifold structure. Then it will be connecting each data point with the nearest neighbors with the strength of the connected determined by the fuzzy membership function. Then it will be learning from the low dimensional embedding. So some of the applications where you can see this dimensionality reduction is data visualization, again the cluster analysis, manifold learning and the feature extraction, we'll be able to see this machine learning or models. That is dimensional. So some of the types of latent space by model is going to be which can be used for the autoencoders, okay, in the GAN networks, in the diffusion models, in the transformers. Okay. Properties of good latent spaces is the good latent space, it has to be continuous. That is, it depends upon the nearby points. So nearby points, so it is going to give you the similar outputs. It is interpretable. Okay. We can easily interpret what it is. Dimension corresponds to the meaningful factors. Okay. Small changes lead to the small changes in the output. Sometimes small changes also some makes a larger changes in the output. Then it is disentangled. Okay, each dimension controls one factor independently. Some of the operations, what is seen in the latent spaces, interpolation. It does a vector arithmetic, words arithmetic. So, for example, smiling woman means neutral woman plus neutral man can be a smiling man. Okay, day image, night image by moving along a direction in the latent space. Then you can go for the editing, modify latent vector to edit the image for the clustering and visual intuition for the image latent space as a map. So when you're going to see it as a map, so mountains can be outlier images, valleys can be a common images, clusters can be a categories, directions can be given as a semantic changes. So this model uses this map to navigate and generate a new data. So some of the real examples you can see is for the prompts, stable diffusions prompts embedded into the latent spaces, it will be decoded into the images. So what we are using the GPT. So here maps, words are mapped to vectors, then that is a transformer model. It is transformed and decoded back to the words. Then for the deep fake models, latent space representation of the faces, which is going to be modified and swapped. In the summary, latent space is a hidden internal space where AI models store compressed meaning of data. This is going to be in the hidden internal space. It is a place where concepts, styles, semantics, structures live. So here in the given, this is a neural network example I have taken. So here we'll be having an encoder, which is going to be the input data. Then this encoded data, which is going to be in the latent space, again decoded, and it is going to be reconstructed data. This is about the latent space. These are some of the references I have taken, some textbooks and from journal papers. And
Thank you, ma'am. Thank you so much.
Thank you
Participants,
for your
participants, if you have any queries, you can post in the chat box. Ma'am,
ma'am, I will stop the sharing of my content.
Yes, ma'am. One question is there, ma'am.
Huh?
Question answer session.
In encoding, it's also called downsampling and upsampling. How to process the video data set. Again, the video data sets will be a frame of data. Frames of data only you will be giving.
Hello.
Yes, ma'am.
And Dr.S in encoding, it's also called downsampling and upsampling. Yes, ma'am.
How we put attendance for this session? Attendance will be posted in the chat box. Attendance link I will post now.
A few of them, few questions.
What is the major difference between autoregressive and moving average? Ma'am, one more question is there. What is the major difference between autoregressive and moving average?
So here the key difference is that and autoregressive model uses past values of the time series to predict the current value, while moving average model uses the past forecast errors, or we'll be terming it as a shocks. So this AR models, that is autoregressive model, it rely on the inertia of the data, whereas moving average models rely on the influence of the past random disturbances, that is the errors, forecast errors.
Oh, it's audible.
Is it audible?
Yes, ma'am. Yes, ma'am. Yes, ma'am. It is audible.
Yes. That is the major difference between the autoregressive and the moving average.
Okay,
Ma'am,
okay.
next question, ma'am. Next question, ma'am. Explanation of VCA. PCA.
Okay. So I think explanation of PCA is very
PCA.
nice with the examples. So they have given that it's nice with example I have taken because I think that model I have given with example. Principal component analysis. So do you want me to explain it again or?
Yeah, sure, ma'am. Yeah, sure, ma'am.
If someone has, what part of maths should they start prioritizing? So I can say for learning artificial intelligence or machine learning, you start with statistics, right from what is an average, what is a mean, mode. You can start from there. It can be with your 8th standard or 9th standard maths, and then probabilities. Statistics, probability.
One more question, ma'am. Is probabilistic generative modeling is heuristic?
Yes, ma'am.
Is probabilistic generative modeling is heuristic?
Probability, as the name says, probability. So you're asking whether it is a futuristic model?
Yes, like that they asked, ma'am.
Yes, it should be, because it enables the machine to create the novel content, so which is going to be like a human-made creations. See, by learning the probability distributions of data, this model can generate the realistic text, images, audio with the advancement of AI. So it is
Yes,
all
ma'am.
the advancement what we are seeing, so like an evolution only. So as I was saying, we had Google translators, right? From in 2006, then autofilling of the words. So generative AI is not a new one. It is not at all a new one. So we have been having our alarm. You will be able to set an alarm for 8 o'clock in the morning. Okay, your alarm is set. Again, this is again a generative AI. So if you want, I can say that AI is going to be 10 stages of AI. So now we are in the 4th stage of AI, that is the generative AI. Next, we'll be having out intelligent AI. So it goes till like godlike AI, transcender AI, cosmic AI, and the last stage predicted is your godlike AI.
Okay. Thank you, ma'am.
So for the query, what they have asked is probability generative model futuristic. It is certainly yes. Okay, so most of the generative models are based on it, based on the probabilistic, and the current and the future advancement of future artificial intelligence is based on this probabilistic model. So any other queries?
I think you answered all the queries, ma'am, almost. Shall we wind
For
up the
those who
session,
are
ma'am?
starting to learn machine learning or AI, if it is going to be a starting time, first you have the underlying mathematics, strong mathematics, and I think it will really help you a lot. So otherwise,
ma'am.
you will be stuck into a loop. Again, you have to come back, learn this and go. So have the fundamentals, basics, and then you can start doing your machine learning.
Yes, ma'am.
Thank you, ma'am, for your fantastic talk on generative model. Your presentation was major highlights, ma'am, and everyone learned so much for your expertise. We truly appreciate you sharing your valuable insight with us. Thank you, ma'am, answering with such clarity, ma'am. Thank you.
Okay, I thank all the organizers, the head of
Thank
the
you, ma'am. Thank
department
you. Thank you,
for the
ma'am.
opportunity given to me. Thank
Yes,
you.
ma'am.
I'll make a leave.
Yes, ma'am. Yes, ma'am. Yes, ma'am.
Yes, ma'am. Thank you, ma'am.